So to build to our modern picture of an atom, I want to talk now about the dual nature of matter because we've already talked about the dual nature of light. And this gets kind of interesting. But I'm going to start with Louis de Broglie. Uh, Again, living, working at the beginning of the 19th century, essentially, um, overlapping actually within my lifespan by a little bit. So de Broglie proposed that particles could have wave-like character. Right? So we've already said that light can behave both as a wave and as a particle. And de Broglie said, well, guess what? Matter, which we're used to acting as a particle, can also act as a wave. And he predicted that the wavelength of a particle would be inversely proportional to its momentum. So if something is very, very, very small, the wave character of it would become significant. And so electrons being very, very, very small would have a significant amount of wave character to their behavior. And that would become a meaningful part of how we see this picture of an atom. So de Broglie was able to develop an equation that relates mass and the speed of a particle to its wavelength. And we get wavelength is equal to Planck's constant divided by mass times velocity. And I know the fonts that I use and that a lot of programs use have velocity and frequency look very similar. And so this one here is velocity, not frequency. So there's that. Be careful. Um, and so let's take a look at an example of this. We're gonna skip this one right here. Um, as an example, and you can try this on your own just to play around with this equation first. But our equation states that we have wavelength equal to Planck's constant divided by mass times velocity. And we know that if we have an electron ejected from a metal foil, right, the amount of energy it absorbs from light that exceeds its binding energy will dictate the amount of kinetic energy it has. And so that will impact its velocity as it travels away from the atom. So we know that we have a velocity equal to 1.15 times 10 to the fifth meters per second, pretty fast. And we want to know what is that wavelength, the de Broglie wavelength for this particle. So we're talking about an electron here, which we have so far understood to be a particle, a very small particle, but a negatively charged particle that has mass. And so if we look at this, we find that the wavelength is going to be equal to that 6.626 times 10 to the negative 34th joules seconds. Good old Planck's constant. We'll use that a lot in this chapter. And then we need the mass of an electron times its velocity. So the mass of an electron, if you go back to chapter 2 when we first started introducing the structure of an atom, we gave you masses for the different particles, the neutron, the proton, and the electron, and showed, look, the electron's really small compared to the neutron and proton. Well, let's bring that back. So the actual mass of that electron is 9.1093836. I just threw a bunch of figures in there, times 10 to the negative 31st kilogram. Okay. So we are going to use units of kilograms because we want to be able to relate this to a joule. And 1 joule is equal to a kilogram meter squared per second squared. So we really want to make sure that our mass is in kilograms for this, and that'll be really key. So taking that mass of the electron, we'll plug it into our mass value. I'm going to cut off some of these figures just so I have enough room on my page to write it. But when I plug it into my calculator, I'll use them all. And then our velocity is given to us as that 1.15 times 10 to the fifth meters per second. And we'll want meters per second because, again, that idea of what a joule is it includes units of meters and seconds. So we don't want to have nanometers or anything like that. And so if we just plug this in, we'll get this wavelength for this electron. And when we do that, we get a value that is 6.325 times 10 to the negative 9th meters. I'm going to convert that into nanometers, since especially when we think about like the visible spectrum, we're thinking on the order of 400 to 700 nanometers. I think it's nice to put this in the context of something that's a bit more familiar to us. So I'm going to multiply this by 10 to the ninth nanometers by 1 meter, just using a simple metric conversion to get 6.325 nanometers. So that's a lot smaller than what we'd expect for something like visible light, right? Which is more like on the order of 600 nanometers. And so that wavelength is really small. So that remember, as we got smaller and smaller wavelengths, we had higher and higher frequencies, which meant we had higher energy. So this electron has a higher energy wave than we would expect for something like visible light or radio waves or something like that.